Welcome. Thanks for coming today. My name is George. I work for the cybersecurity research group here at Southampton University. I'm a PhD researcher. My research focuses on the decentralization of the DNS protocol. So, as you can imagine, it has to do with decentralization, distributed systems, and all of these interesting things. And that's the reason I decided today to present this very, very interesting topic called practical Byzantine fault tolerance. So today we're going to introduce a concept. This is actually a failure concept. And then we're going to discuss the solution for this failure concept. And of course, I'm talking for the Byzantine fault tolerance and the practical Byzantine fault tolerance, respectively. So let's see what we're going to talk about today. So we're going to start with some terminology. So I'm going to explain some definitions that I'm going to use a lot during this presentation. Then we are going to talk about the problem, which is called the Byzantine fault tolerance. And then we're going to introduce the solution to this problem. And in the end, we're going to see some outcomes. When I say outcomes, I mean some reasons why this algorithm is so popular, why this algorithm works, and why do we use this algorithm. So what we won't talk about today. So I'm not going to go through extreme implementation details. So we're just going to see the backbone of the practical Byzantine fault tolerance algorithm. I'm not going to talk about engineering challenges. And I'm not going to talk about cryptocurrencies and financial things. And of course, I'm not going to talk about trading. So please don't ask me about trading things like what's going to be the Bitcoin price. I'm not here to give you financial advice or anything like that. Cool. So let's start with some definitions. So let's first understand what's the difference between distributed systems and centralized systems. So let's start with centralized systems. So in this figure, on the left side, you see a centralized system. So this, anyway, these blue dots represent the participants or the users of the network. And as you can see, all these participants are connected to a central entity. So this can be a server or, in general, a central entity. So this is a centralized system. And centralized systems, you can find them in everyday examples, like when you request Google, for example, or Facebook, you actually request their server and they give you back a response. So now we have on the right side of this figure, you see a distributed system. So the difference here is that all these blue dots that represent the participants are connected to each other instead of a centralized entity. So all these participants are connected to each other and they work together in order to achieve a common goal. So this is the difference between the centralized and the distributed systems. Let's talk about consensus now. So what is consensus? In general, what is consensus? Consensus is something that we use, again, in our life every day. So consensus can be found in a simple decision. So for example, if you chat with your friends about where you are about to go for holidays, for example, you need to agree on the same destination. So you agree on this destination, so that means that you have reached consensus. So the same happens in systems and in networks in general. So in networks, and specifically in distributed networks and distributed systems, consensus is the process of agreeing on a common decision. But here in systems, we add an extra thing, agreeing on a common decision, even in the presence of faulty nodes. And we're going to see what faulty nodes mean. Now, how does consensus apply to technology? So where can we find consensus? We can find consensus in cryptocurrencies and blockchains. So for example, Bitcoin uses a consensus algorithm to agree on the sequence of the transactions. We can find consensus in IoT networks. So all these devices, these smart devices, need to come into an agreement in order to take some actions. And we can find consensus also in supply chain. All these machines, they need to communicate with each other and again take some decisions in order to come up with a final product. So consensus can be found in almost everywhere. Now, what's the problem with the consensus? Let's start by defining the problem. So, on the left side, on the right side here, you see a network. This is again a distributed network. We're going to use distributed networks today for our examples and for everything that we're going to discuss. So, what is the problem with consensus in distributed networks? The problem with consensus is that in these networks, there might be some nodes, some participants that do not perform properly. And what does that mean? That means that some of those participants might be flaky nodes, which means that these participants run an outdated version of the protocol, or are not connected properly to the network, or I know they have a very slow internet connection. These are the flaky nodes. So these are the nodes that face technical issues and they don't run the protocol properly. And we might have also malicious nodes. This is very self-explanatory. Malicious nodes are all those nodes that try to negatively impact the decision of the network and cause, let's say, confusion. So this concept is called Byzantine failure. So Byzantine failure is the scenario where we have those kind of nodes, and those kind of nodes, we call them Byzantine nodes. So whenever I use this term, Byzantine nodes, I refer to either flaky nodes or malicious nodes within a distributed network. Now, what can cause all these failures? What are the problems that can cause these failures? So this is what I call a failure classification. And let's go through these problems. So first of all, can all nodes see all messages? So if not, that means that some of the nodes are not participating in the consensus protocol. Do nodes fail? If yes, that means that again, some nodes are unable to participate in the consensus protocol. So what about the number of these Byzantine nodes? Is the number static or dynamic? So does it mean that do nodes increase, or are they static, the number? Are the nodes fully connected? Because if they're not fully connected, that means that they can decide or they can receive others' decisions. What about the algorithms that these nodes use? Are they random, or can we predict the pattern behind those algorithms? And finally, do those nodes use quantum or binary computing? Because if they use quantum computing, that means that they have an advantage and they can calculate more complex things easier. So all these concerns lead to what we call failure. Now, let's start by defining the problem with a very simple example. So imagine that we have an army, and this army has two leaders, leader A and leader B. And those two leaders want to decide whether they attack the enemy army or not. That's very simple. So if leader A decides to attack and leader B decides to attack, then that's fine, they attack. If leader A decides to attack, but the leader B does not, they don't attack, because the enemy army is bigger and they will lose. So in order to attack, they both need to decide to attack. So leader A and leader B communicate by sending couriers. And unfortunately, these couriers pass through the enemy territory, which means that there is a chance that these couriers might not make it. So I want you to think of a simple protocol, a simple sequence of steps through which those two leaders can decide whether they attack or retreat. Just think something very, very simple. What do you think?
Yeah, they may send like a confirmation, for
Mhm.
instance.
Yeah, okay.
Well, they can only attack if they both receive an attack message from each other.
Mm-hmm.
Otherwise, they're stuck in retreat kind of mode.
So yeah, leader A has to take a decision. It needs to communicate with leader B, and then leader B somehow needs to communicate with leader A. either to accept this decision or reject this decision.
Yeah.
So how can those two communicate? What messages should they exchange
Well,
to reach a common agreement?
well, the first one should say, I want to attack. If you want to attack, I'll do it.
Mm-hmm.
And then wait for the response from leader B. If leader B is positive, then you can do it.
Okay.
So you're only having to send like 2 messages.
Cool. Yeah. Okay. That's fine. So what you try to explain and what you said is actually pretty close to a protocol that's called three-way handshake, and this protocol is used by TCP. So this actually involves the exchange of 3 messages. So leader A wants to attack, and it sends a response to, it decides to attack, so it says to leader B, if you respond, I'll attack. Now, leader B receives this response. So leader B says, okay, I want to attack too. So it replies back to leader A, if you respond, I'll attack. So at that point, leader A has committed to attack, but leader B hasn't yet committed to attack, because leader B waits for a response from leader A. So now leader A will send back the response and say, we'll attack. So now both of the leaders have committed to attack. So what's the problem here? What if this message never reaches leader B? Leader A has committed, leader B has not committed yet, so they can't decide whether they attack or not. So that's the problem. That's the problem with the two generals problem. The problem is that this algorithm is a sequential algorithm, and if we miss a single message, the whole process breaks, the whole algorithm breaks. And this is why we say that the two generals problem doesn't have a perfect solution. Now, this paper, the Byzantine generals problem, was introduced back in 1982 and answers exactly this question. How many Byzantine nodes can a system survive, and how do we build such a network? So we saw an example with 2 leaders, with 2 participants. So this paper makes this scenario more generic and answers the question, what happens in a bigger network? What happens with more nodes and more failures? And let's see what does it mean. So imagine now this scenario. We have a bigger army with 5 leaders, and they want to decide whether they attack the fortress or they retreat. So let's assume that these are the decisions that they take. So 3 of the leaders say, we attack, and 2 of the leaders say, we retreat. Well, we come up with this vector, and this vector is actually a representation of their decisions. So 3 attacks, 2 retreats, the majority wins, the army attacks. Now, let's assume that this leader is a traitor. And we don't really care what the traitor thinks. Only thing we know is that the traitor thinks evil. So if the traitor says attack, then we have 3 attacks, 2 retreats, the army will attack. If the traitor thinks retreat, we have 3 retreats, 2 attacks, the army will retreat. The problem would be if half of the leaders would think attack and half of the leaders would think retreat, because in that case we wouldn't have a consensus. So the question here is, how many traitors do we need in a network in order not to be able to reach consensus? And let's take some cases. So let's say for a network with 1 participant, in that case, this participant can be an honest leader or a traitor. So again, there is no consensus, because if it's a traitor, it decides whatever he wants. There is no consensus. In a network with 2 participants and 1 traitor, again, we don't have consensus, because if we have 1 honest leader and 1 traitor, if the honest leader says attack, the traitor will say retreat, so there is no consensus. So what happens in a network with 3 participants? So let's assume that all the 3 participants are honest. And we also assume that this is the leader of the army, and those two are the lieutenants. So if all these participants are honest, the leader will say attack to both of the lieutenants. Then the lieutenants will exchange what they've heard from the leader, and they will come up with this vector. So this means that, okay, my leader says attack, my peer lieutenant says attack, so I'll attack. And the same happens for this lieutenant. So what happens if one of these lieutenants is a traitor? So in that case, the leader will say to both of them, attack. But this traitor, when it comes to exchange what he have heard from the leader, is going to change the decision. So it will say, okay, I've heard attack, but I'm going to say I've heard retreat. So in the end, this lieutenant here will say, okay, my leader says attack, but my peer lieutenant says retreat. So what am I supposed to do?
Does the time matter here?
No, the time doesn't matter, and we're going to see why later. And the same case can happen. The same thing can happen in this case, if the leader is a traitor. So if the leader is a traitor, might say, okay, I'm going to say retreat to one of my lieutenants and attack to the other one. So in the end, this lieutenant will say, my leader says attack, but my peer lieutenant says retreat. And this lieutenant will say, my leader says retreat, but my peer lieutenant says attack. So what am I supposed to do? So how many traitors do we need in a network of 4, 5, or a network of n participants? Well, this paper answers this question, and the answer is given through this lemma. And this lemma says that if 1/3 or more of the participants of the network are malicious, then we can't have consensus. Then our network is not Byzantine fault tolerant. So that means that in order for a network to be Byzantine fault tolerant, 2/3 of the participants should be honest. And if you don't believe this lemma, we can simply prove that. So if we take this example that we saw before, the one with the 3 participants and the 1 traitor, if you apply all these numbers, so all these numbers to this proof, this equation here should be satisfied. So 3 times 1 plus 1 gives us 4. 4 is greater than 3, so there is no solution. So that's why we need 2/3 of the network to be honest.
So if not,
Mm-hmm.
if not the 2/3 are not honest, what will
Mhm.
happen?
That means that the traitors, the malicious nodes, can decide whatever they want, can impact the network.
So how can we make sure that the network, or 2/3 of the network are honest?
We can't. We assume that.
Okay,
This is an assumption.
assumption.
So, based on this lemma, we have lots of different solutions. Lots of different papers that address this problem, how to implement a Byzantine fault tolerant network. So the one I want to introduce today is called practical Byzantine fault tolerance. And the difference here is that this algorithm is practical, and this answers actually your question. So this algorithm, we need to makes 3 assumptions. So the first assumption is again that 2/3 of the network is honest. It also assumes that the network is asynchronous, and what asynchronous means, that means that the communication between the nodes doesn't follow any synchronization in terms of time. So that means that you can set up and run a node here in the UK, and there might be another person running a node in China, for example, where the time is different. And you can both participate at the same time in the consensus protocol. And of course, the set of participants in the system is known and fixed. So that means that at a specific point of time, all the participants of the network know exactly how many nodes and how many participants there are in the network. So these are the three assumptions that the practical Byzantine fault tolerance algorithm does. So these are two more terms. That's the last two terms, I promise, I'm going to use. It's very simple. Replica R means the nodes of the network, so it's the participants of the network. And then we have the primary replica. The primary replica is a special node that, which is chosen randomly from the network and is responsible for coordinating the algorithm. So let's explain this algorithm. Let's explain how this algorithm works through an example. So imagine this network with those 5 participants. So this is the client. This is the client that wants to send the message to the network. And this is our primary replica. And R2, R3, and R4 are the rest replicas of the network. The primary replica, as I said before, is chosen randomly, and each time that the algorithm runs, the primary replica changes. Just to make sure that if the primary replica is a malicious node, next time it won't affect the consensus. So the practical Byzantine fault tolerant algorithm has 3 phases. The first phase is called pre-prepare phase. So in this phase, the client sends the message to the primary replica, and the primary replica broadcasts the message to the whole network. That's very simple. So all the network now has the message. The second phase is called prepare. And in this phase, the replicas that now have the message validate the message. So all these replicas run the exact same verification algorithm, and they run the verification to see if this message that they have received from the primary replica is valid or not. So once they're done, once they verify the message, the primary replica waits for 2/3 of the replicas to agree on the verification. So that means that 2/3 of the replicas should say the same thing. And why 2/3? Because we said that 2/3 is the number of honest nodes in a practical Byzantine fault tolerant network. So once those replicas have verified the message, we are getting to the third phase, which is the commit phase, and simply send a commit message back to the primary replica, meaning that, okay, the message has been verified, the message is valid, and you can now distribute it to the rest of the network. So the reasonable question here would be, what if the primary replica is a malicious node, is a malicious user? So let's go through each phase and see what happens. So in the pre-prepare phase, the client will send the message to the primary replica, and the primary replica will modify this message. Now, in the second phase, the prepare phase, the replicas will try to verify this message, but the verification will fail because we said that 2/3 of the replicas are honest, so they will understand that someone has modified the message. So they won't verify the message. And that means that in the third phase, they will never send the commit message back to the primary replica, so the modified message will be never broadcasted to the network. Yeah.
Sorry, but how do they know that it's been modified, like through cryptography?
So this verification algorithm is different. I mean, the thing is that all these replicas use the same verification algorithm. It can be a cryptographic verification algorithm, it can be something else. It doesn't really matter. The thing, what matters is that they all run the same algorithm. But yeah, in most cases, it's a cryptographic algorithm.
But everyone modifies the content for the 3 of the nodes, or just for some of them?
So the message is modified here.
Yes, is it modified and then transmitted the modified message to the 3 nodes, or just like, it transmits the modified one to just 2 of them, and then the original
No, the modified message is transmitted to all the nodes of the network, yeah. But if 2/3 of the network says that we can't verify this message, that means that this message will never be broadcasted, because they will never send back the commit message.
Right.
I see that like R1 like modifies message in some way, and then all the like clean nodes in the network.
So in which phase?
Yeah, in that phase, all the next like nodes say, well, we can't verify this because we know you've modified it in some way.
Exactly.
And I see, and then they send it back to R1, and then
if they decide that the message is modified, they will never send it back to R1.
yeah,
So the modified message will never get back to R1. So they will never send the commit message. The commit message means that you're ready, you're free to broadcast the message to the network.
yeah,
So in the end, R1 will never receive this commit message.
yeah.
So it will never be able to broadcast the modified message to the network.
But what if R1 just pretends it's received the commit message, then proceeds to like go to the next phase?
So what do you mean?
What if because like R1 receives some commit messages from R2, R4, and R3
Mhm.
if it isn't modified, but say it is that they don't send commit messages, can't R1 just pretend it's received the commit message and then do the next phase?
Well, let's say
I misunderstood.
okay, so you mean that R1 says, okay, even I won't get the commit message, I'll pretend that I've got it,
Yeah,
and I'll proceed to the next phase.
yeah,
No, that can happen because R1 is just one node, is less than 2/3.
I see. Oh, of course, yeah,
Yeah.
yeah, that makes sense.
This is the most important assumption we make.
Yeah,
If this is not, if this doesn't happen, if not 2/3 of the network are not honest, this algorithm cannot work.
yeah,
That's the most important thing. But again, this is an assumption. I'm getting back to your question. We can't really say that we can have such a network. It's an assumption.
mm.
I think in real life we have to make the 2/3.
In real life, yes. But you never know, especially if you are creating, let's say, for example, a blockchain network from scratch. Your blockchain network will not be very popular.
Yeah.
So you won't have enough nodes. So it is very, very easy for a malicious user to create 100, for example, malicious nodes
So I think
and register.
the solution for this is to create a private or permission blockchain.
Yeah, this is a
So
solution.
You can control them.
Exactly. This is one solution. It's called like identity verification or things like these. Yeah. But yeah, in public blockchains where you don't have verification.
It's like XRP. XRP is Ripple is
Yeah. Yeah, Ripple, Bitcoin, all of these networks are public, you can't prevent that. But all of these blockchain networks have enough nodes, and most of these nodes are honest. So you can't actually create more than 2/3. It's almost impossible.
With dishonest nodes, they have to all be in agreement with each other as well, can't they?
Yes.
That's the other thing. Like, so you have to have a third of all users conspire together to do this message. You can like if each one wants its own game, like some may want to attack and others may want to retreat if they're dishonest. That doesn't make any difference. It's only when they all say the same thing.
Yes, exactly.
Yeah.
Because they all run the same verification algorithm.
Mm.
So if they are honest, that means they haven't changed the verification algorithm. So they all run the same thing.
Yeah.
In the end, they will take the same decision.
Mm.
Yeah. So this is how practical Byzantine fault tolerance algorithm works. And this is what happens in case of a malicious replica. But again, remember that in each consensus cycle, the primary replica changes, just to make sure that if replica is malicious, next time another one will be chosen randomly, and hopefully it won't be malicious. Right, so now, why is this algorithm important? Why this algorithm is important in real life scenarios? So first of all, the first property of this algorithm is that it offers high security, which means that by using the practical Byzantine fault tolerant algorithm, we can ensure that transactions are tamper-proof. That means that transactions cannot be modified, even if there are malicious users in the network. And why does that matter? Because applications, real-life applications, require a high level of security. So imagine, for example, financial systems like Bitcoin, how important it is for these systems to make sure that transactions cannot be modified. And this is what practical Byzantine fault tolerance offer. Fault tolerance. So this actually, this is related with the reliability and availability of the system. So fault tolerance ensures that the system can function properly, even if there are malicious users in the system. So again, that makes the system more reliable and more available. And in the end, deterministic consensus. So that means that all the nodes in the end will decide on exactly the same thing. And this actually, this is very important because it gives us predictable outcomes. And this is important for, again, systems that they work with transaction histories. So Bitcoin, for example, if you send some money to someone else, and after 1 year, you come back and say, I didn't send this money. So people, other nodes, participants, even outside of the network, will be able to go through the transaction history and see if you are lying or not. So this is what deterministic consensus means. And again, this is something very, very important in these kind of systems. Right, so let's do a recap. So we started by introducing the Byzantine failure. So we saw what a failure is and what are the different ways to that lead us to this failure. We talked about two different Byzantine nodes. We talked about the flaky nodes, which are nodes that do not run the protocol properly. And we also talked about malicious nodes, which are nodes that they want to negatively impact the network. And then we introduced the problem. We started with a very simple example, with a two generals problem. We proved that this problem is not solved because the process is a sequential process, and if a single message, if we miss a single message, the whole process, the whole algorithm breaks. And then we introduce a more generic image of this problem, which is called the Byzantine fault tolerance. And we, again, prove that if not 2/3 of the network is honest, then our network cannot reach consensus, cannot be Byzantine fault tolerance. And in the end, we said, we briefly discussed why this algorithm is important, why this algorithm is popular, and how this algorithm applies on everyday technologies. So these are the references I've used for this presentation. So the first one is the paper that explains the problem, the Byzantine fault tolerance problem, and the second one is the official paper that explains the practical Byzantine fault tolerance algorithm. So if you want to find more technical details, more mathematical proven details, you can just go through this paper. And yeah, that takes me to the end of my presentation. So thank you very much for your time. So if you have more questions, I'm happy.
Yeah, thank you.
Thank you guys.